Hey everybody. So we're getting into 4.4 part 1 today, looking at the Pythagorean theorem. This is probably a little formula that you've seen in the past. But for now, go ahead and get this title, draw this triangle, and then I'll show you the actual theorem. Okay, so let me scroll up there. So there is the Pythagorean theorem down on the bottom. C squared equals a squared plus b squared. First thing to maybe notice, when you learned this in the past, you probably learned it like this. A squared plus b squared equals c squared. Okay, this is exactly the same way that I teach it, but I put c squared first because it helps later on down the line when we have problems that are a little bit different. Okay, but just know the way you learned it in the past and the way we're learning it now, it's the same thing, just the two sides of the equation are flip-flopped. Okay, so that's the Pythagorean theorem. And if you guys remember, the purpose of the Pythagorean theorem mostly is to find missing sides of right triangles. Okay, and you can see up here, this right here is considered a right triangle. The reason why it's a right triangle is because it has a right angle in it, a 90-degree angle. Okay, and with that information, we can, if we're given two sides of a right triangle, we can find the missing side by plugging them into the Pythagorean theorem, doing a little bit of math, and going from there. Okay, so this is going to be a nice little review. We're going to be, seeing right triangles throughout the year. You can imagine we have lines that cross one another, and they cross sometimes at a 90-degree angle. And what if we had another line that crossed like this? Well, if you notice, we have a right triangle right there, and we could potentially find a missing side of it using Pythagorean theorem. So that's kind of how it works with what we've been learning recently. Okay, so yeah, with that, let's go ahead and jump into it. Okay, go ahead and take a moment, copy this slide, and we will find the missing side line. Okay, so it says find the missing side of each triangle. First thing, we have a right triangle. We're given two sides of it, and we're asked to find this missing side. All right, real quick, let me flip back to the last slide. When we're plugging our numbers into the Pythagorean theorem, here's the big thing to remember. The C value is always a certain side of the triangle. Okay, and C value is always the side length that is called the hypotenuse of the right triangle. The hypotenuse is the longest side of the triangle. Here's the easiest way to identify which side is the hypotenuse. It is always going to be opposite this 90-degree angle. You'll see me draw an arrow across from the 90-degree angle. It will always point at the hypotenuse, and that's always the first number that we'll plug in, or sometimes it'll be the variable. Sometimes it'll be the thing we're looking for. Okay, A and B, the other two sides, are just that. They're just the other two sides. It doesn't matter which one you plug in for which, but normally I'll make the smaller of the three A and then the next biggest one B. But just know it doesn't really matter. You can't really mix up A and B. C is the one that really matters, making sure you get that as the hypotenuse. Okay, so with that said, here's what I noticed. The side length that we're looking for on this problem is opposite my 90-degree angle. It is the hypotenuse of my triangle. Okay, so let's first write out the Pythagorean theorem again. So c squared equals a squared plus b squared. Okay, and let's plug in what we have. Okay, we're looking for the hypotenuse, which is always what we plug in for c. They're calling it x, so we're going to do the same. Okay, A and B are the other two side lengths. Okay, again, it doesn't matter which one I plug in for which, but normally I'm going to make A the smaller of the two. So I'm going to plug in 6 for A, and I'm going to plug in 8 for B. Okay, and you guys might notice there's units, it's miles, which is, this is a really big triangle. When we plug in numbers, don't worry about the units. We'll add them in at the end when we get our answer. Okay, so here's our equation we need to solve. Okay, first things first is we need to square these numbers that we can. X squared, we're going to solve for x eventually, so we're going to leave it as x squared. Okay, but let's go ahead and square these numbers. If you do not have a calculator yet, I highly recommend getting on like Amazon or going to Walmart or whatever and buying yourself a cheap scientific calculator. Okay, just a little reminder, that's a calculator that has the sine, cosine, and tangent buttons. Okay, you can also search for one on your phone. I'm sure they have a free one. You can search online. If you Google scientific calculator, one will pop up for you. There's a bunch of different ways, but having an actual calculator is going to be really nice starting now. Okay, so yeah, squaring these numbers, you can maybe do some of these in your head. 6 squared, 6 times 6 is 36. 8 squared, 8 times 8 is 64. Okay, now we can combine these together, add them together. 36 plus 64 gives me 100. Okay, so I have x squared equals 100. Okay, just one thing to realize, we have not solved for x yet. We need to get rid of this power of 2. Okay, and if you guys remember, whenever we're solving and we're trying to get rid of numbers, we have to always do the opposite operation, right? Like if something's being multiplied, we divide to get rid of it. Okay, what do we do if we have a number being squared? How do we get rid of a square? Okay, well, the opposite of squaring is actually square rooting. Okay, so to undo this power of 2, we're going to take the square root. Okay, and again, those are opposites and they actually cancel one another. Okay, but whatever I do to one side, right, I have to always do to the other. Okay, so one thing to just start to memorize, whenever you're solving and you need to get rid of power of 2, you're going to take the square root. Okay, and what I normally do is kind of cross them out, just showing, okay, the square root and the power of 2, they cancel, and now I have x by itself. Over on the right, I have the square root of 100. Okay, and again, this is where sometimes the calculator is going to be nice. This is a perfect square. You might already know the square root of 100 is 10, but if you don't, you need a calculator to be able to type this stuff in. Okay, so I'm getting 10. Okay, a couple by the ways. Technically, when you take the square root of a number, you're getting the positive and the negative as the answer. Technically, the square root of 100 is actually a positive 10 and a negative 10. Okay, but since we're talking about the lengths of sides, it doesn't make any sense for them to be negative, 10 miles long. So we ignore the negatives. That's why we're just putting a positive 10. Okay, that's just the technicality, but I wanted you to know. Okay, and then the last thing, we have units, so let's go ahead and add them in. 10 miles. All right, here's something I always suggest with, Pythagorean theorem problems. After you get your answer, look to see if it makes sense in the context of your triangle. Okay, this is the hypotenuse, the longest side of my triangle, and it's 10 miles. Does that make sense? Yeah, it does, because this side is 6 and this side is 8, so it makes sense for the longest side to be 10. Say, for example, we got our answer as 4 miles. Would it make sense for the longest side to be 4 if this side was 6 and this side was 8? It wouldn't. Okay, so just make some sense out of your answers and see if they work. Okay, let's keep going. All right, let's go ahead and try another one here. Same directions throughout most of this lesson. You don't need to keep copying those. Go ahead and get this triangle. All right, so first things first. What side length are we looking for? Well, obviously, we're looking for this one here. All right, when we go to plug in our numbers, here's what I notice. On this problem, we have our hypotenuse. Okay, we have the longest side. So again, let's go ahead and write out the Pythagorean theorem again. C squared equals a squared plus b squared. Okay, remember, the hypotenuse always gets plugged in for c, and we know it on this one. So we're actually plugging a number in for c. Okay, a and b are the other two sides. It doesn't matter which one I plug in for which. I'm going to make 9a, and I'm going to plug in with the side length we're looking for b, x. Okay, so just one thing I want you to realize. On this problem, we knew the hypotenuse. We plugged in 15 for c. On the last problem, we didn't know the hypotenuse. That's why we plugged in x for c. Okay, so don't think x is always being plugged in for c. It really just depends on the problem. Okay, so now we just need to solve this thing. We've got some squaring to do. So calculator is your friend. 15 squared is 225. 9 squared is 81. And then we'll bring down this x squared. Okay, we're solving for x, right? We have these two numbers to get rid of. Before we can get rid of this power of 2, we need to deal with this 81, right? It's technically being added, so we're going to subtract it from both sides. So 225 minus 81 gives me a 144. Over on the right, now I just have that x squared. Okay, last step. Now I can get rid of this power of 2. I'm going to undo the squaring with square rooting. Whatever I do to one side, I do to the other. Okay, so on the left here, this is where you might not have memorized this, the square root of 144. It's actually another perfect square. If you type it in, you're going to get that the square root of 144 is 12. Okay, over on the right, these cancel. We got x. Okay, and then I'm going to go one more step and flip it around. X equals 12. And it looks like our units are kilometers, so km. Okay, real quick, let's just see if this makes sense. If my longest side length, my hypotenuse is 15, does it make sense for this side to be 12? Yes, it does, right? And this one's 9. So one other thing to point out, we won't use these words a lot today, but we will in the future. This is considered the hypotenuse. These two other side lengths here and here are considered the legs of the triangle. Okay, so this is the hypotenuse. And actually, let's go back to the very first slide. Let's put that on this. Okay, so let's go ahead and point out hypotenuse. I think that's how you spell that. Yeah. So that this is the hypotenuse, and these two sides are the legs. Okay, put that on the very first slide, just because those are words you're going to run into. So might as well do it now. Okay, so anyway, going back to this, I'm gonna have you guys go ahead and try out a couple of these problems, same directions, you don't need those. Go ahead and copy these two triangles, use the Pythagorean theorem to find the missing side lengths. All right, so let's go ahead and try this first one together. First things first, I notice the hypotenuse is what we're looking for. All right, so when I write out my Pythagorean theorem, c squared equals a squared plus b squared. All right, c is always the hypotenuse, and on this one, that's what I'm looking for. That's my variable x. Okay, the other two legs of the triangle, 5 and 12, are a and b. Doesn't matter which you plug in for which, but I'm going to make 5a and 12b. Okay, so on this one here, not a whole lot to do yet. We just need to square these numbers. So 5 squared is 25, 12 squared is 144. Okay, going down, we have x squared equals 25 plus 144. I'm getting 169. Okay, now finally we can solve for x, getting rid of that squared by square rooting both sides. Okay, they're gone. I have x equals the square root of 169. Just so happens to be another perfect square, which, by the way, remember, perfect square is just when we take the square root of a number, we get a nice clean number. Okay, the square root of 169, if you type it into the calculator, should give you a nice clean 13. Okay, we won't always get perfect squares on this step, just so you know. We will eventually not, and having a calculator to get your answer will be absolutely necessary. Okay, but yeah, it looks like our units are meters. There we go. Okay, real quick, does it make sense for our hypotenuse to be 13 if my short leg is 5 and my long leg is 12? Yep, it does. Okay, moving on to this one here. Again, let's write out the Pythagorean theorem. C squared equals a squared plus b squared. Okay, on this problem, I notice the hypotenuse opposite my right angle is 5. Okay, that's what I'm going to plug in for C on this one. Okay, the other two legs are A and B. I'm going to make X A, and I'm going to make 4 B. Okay, so we got some solving, or I guess some simplifying technically. 5 squared is 25. Bring down the x squared. 4 squared is 16. Okay, be careful on this kind of stuff. I always see people think like, oh, 4 squared is 4 times 2. It's 8. No, it's 4 times 4, right? So be careful. Okay, from here, now we can start solving. We need to get rid of the 16 first by subtracting it. All right, so let's see, that cancels out the 16s, bring down the x squared. Okay, over on the left here, looks like I'm getting a 9. Okay, last step is getting rid of the power of 2 by doing the opposite, square rooting both sides. Okay, and square root of 9 is another perfect square. You might have this one memorized, it's 3. So we're getting 3 equals x, or flip it around, x equals 3. Okay, and units, centimeters. All right, does it make sense? My longest side, my hypotenuse is a 5, my short leg is 3, long leg's 4. Yep, that makes sense. Okay, so let's keep going. These problems are basically just going to get a little bit more complicated. Here's this one is, find the missing side just like the others. This one says leave your answer in the simplest radical form. Okay, so we'll see what that means when we get to it. So yeah, go ahead and copy this triangle and we'll solve. Alrighty, so again, I'm going to write out the Pythagorean theorem just so we can get this thing memorized. C squared equals a squared plus b squared. All right, so yeah, first things first, go ahead and plug in your hypotenuse in for C. Okay, hopefully you noticed the hypotenuse opposite this right angle is 7. Okay, so I'm plugging in 7 for C. Other two sides are A and B. I'm going to make 2A. I'm going to make XB. All right, and yeah, let's go ahead and see what happens. We have 7 squared, which is 7 times 7, 49. 2 squared gives me a 4. And bring down the x squared. Okay, from here I can start solving. 4 is being added, so I'm going to subtract it. And it looks like I'm getting a 45 equals x squared. Okay, almost last step here. To get rid of the power of 2, we're going to take the square roots. We have to do it to both sides. Okay, so here's the thing. On this problem, it said leave your answer in the simplest radical form. Okay, on this problem, they don't want us to type this into a calculator and get a decimal as an answer. They want us to simplify this radical. Okay, let me show you how to simplify radicals. It's actually a pretty simple process. Here's what we're going to do. We're going to take this square root of 45. Actually, we can do it right here. And we're going to break it down into its prime numbers. Basically, what are the numbers that are multiplying together to get 45? Okay, well, the first thing we got to just think of is what two numbers multiply to get 45? Okay, there's multiple answers to that question, all right? But you can do whatever comes to mind first. What comes to mind for me is I know that 9 times 5 is 45. Okay, so those are my two numbers I'm going to use. By the way, when you guys break these numbers down, I suggest putting the smaller numbers on the left and the bigger number on the right. Okay, so 5 times 9 gives me 45. Okay, here's the thing. 5 is a prime number. What that means is it can't be broken down anymore. Okay, no two numbers multiply to get you 5, at least no nice clean numbers. Okay, so that's a prime number, but 9 isn't. We can actually figure out that 9 breaks down into 3 times 3, right? Okay, when you break a number down, cross it out. That 9 no longer exists. It's now a 3 times 3. Okay, by the way, these 3's are also now prime numbers. We cannot break them down any farther. Only 1 times 3 would give us a 3, but that doesn't, break it down. Okay, so yeah, these are the prime factors of 45. Here's what we do with them. We're looking for pairs of numbers to take out of the radical, and if the number does not pair up, it stays inside the radical. Okay, when I say pairs, I mean 2 of the same number. So I'm looking down here and I'm noticing, oh, we have 2 of, 3's. Okay, so there is a pair of 3's. Okay, I'm looking at this 5 and I'm thinking, is there another 5 to pair it up with? No, it's by itself. Okay, so I circle pairs of numbers. I underline numbers that do not pair up. Okay, here's why we're doing this. Pairs of numbers. This pair of 3's means a 3 comes out of the radical. Okay, just 1 3, not 2 of them. Pair of 3's means a single 3 comes out. Whatever doesn't pair up stays inside the radical sign. Okay, so that 5 is going to stay inside. Okay, and that's actually my answer. 3 square root of 5 is the same thing as the square root of 45. Okay, it's just a simplified form of the radical. Okay, and I'm going to flip it around. So 3 square root of 5. Okay, and technically yards. Okay, so this is kind of a way for you guys to practice simplifying radicals, something you probably haven't done in a long time. Also, one thing you'd want to do is potentially type this into your calculator and see if you get an answer that actually makes sense. All right, and see that you actually know how to type this in. You need to find the square root button on your calculator. This is stuff that you're just going to have to kind of figure it out on your own because I'm not here to help you with it. Okay, but yeah, try it out. Go ahead and type 3 square root of 5 into your calculator. When you do, you're going to get 6.7082. It keeps going on forever. In this class, if we're asked to have a decimal, normally we'll round to 1 decimal place called the tenths. Okay, and if you guys remember, it's all dependent on this number, whether it stays this number or rounds up to the next number. Okay, if this was a 5 or more, we would round the 7 up to an 8, but it's not. So just so you know, we'd keep this as a 6.7. Okay, but the whole point is does that make sense? If my hypotenuse is 7, does it make sense for this to be 6.7? Yeah, it does. Okay, so just another way of just checking your answer. All right, cool. Let's try another one of these, find the missing side. We got some weirder values here, but don't be afraid. I'll show you what's going on. Try it out. Okay, so on this problem here, let's go ahead and just do what we've been doing. Let's write out the Pythagorean theorem, c squared equals a squared plus b squared. Okay, on this one, I noticed that my hypotenuse, what I'm going to plug in for c, is this number, square root of 13. Okay, don't forget, there's still that power of 2. Okay, a and b are the other two sides. I'm going to make x a, and I'm going to make b this 2 square root of 3. Actually, let me write that a little better. Okay, here's the thing. This whole thing is being squared, so I'm actually going to put parentheses around it to show that the whole thing is being taken to the power of 2, not just the square root of 3. Okay, so this looks crazy, right? You're probably like, oh, this is not looking fun. Here's the good news. Whenever we have square roots that are being squared, if you guys remember, they are opposites. They cancel one another out. So this square root and this power of 2, they're canceling each other out, and we're just left with what's underneath the radical. So we have a 13 on the left. Okay, on the right, we have the x squared. Okay, and this over here is kind of the same idea. Here's the thing though, both of these numbers here are being squared. This 2 is being squared, and the square root of 3 is being squared. And we have to do them both. Okay, so let's start with this. 2 squared, 2 times 2 gives me a 4, so we have this plus, we have a 4. Okay, the square root of 3 squared, just like before when this radical and power of 2 canceled, the same thing is happening here. These are canceling, and we're left with what's underneath the radical. Okay, so we're just left with a 3 here, and these two numbers are being multiplied together. Okay, so yeah, this looked crazy, but it was actually kind of nice because the square root or the radical signs and the power of 2s, they're canceling. We end up with pretty simple looking numbers. Let's multiply these together. So we have a 13 equals x squared plus 12. Okay, now we can just go ahead and solve like we were before. We got to get rid of this 12 by getting rid of it, subtracting it. Okay, looks like we get a 1 equals x squared. Okay, now finally we can get rid of this power of 2 by again taking the square root of both sides. All right, square root of 1, you could plug that in, but you might already know it's actually a perfect square. The square root of 1 is 1. Okay, so we're getting 1 equals x, or flip it around, x equals 1, and it looks like our units are miles. Okay, so 1 mile. Okay, so I'm gonna have you guys go ahead and try a couple of these on your own, same directions. Okay, try these out, and then we'll go over them. Go ahead. All right, so on this first one here, I guess first of all, let's go ahead and write out, too far. Let's go ahead and write out the Pythagorean theorem, c squared equals a squared plus b squared. Okay, on this problem, it looks like our hypotenuse, the value we're plugging in for c, is going to be x. Okay, other two legs of the triangle look like they're both 7s. Okay, so let's see what happens here. We have x squared equals 7 squared is 49, plus 7 squared is 49. Okay, so it looks like we're getting x squared equals 98. And solving for x, taking the square root of both sides, right? So here's the big thing. Square root of 98 is not a perfect square, and they want us to write it in its simplest form. So we need to break down the square root of 98. So let me make some room here. All right, so again, when we break down when we simplify a radical, we're breaking it down into its prime numbers. The first thing we need to think of is what are two numbers that multiply to get 98? Okay, here's the thing. You might not immediately think of it. Okay, but if it's an even number, you know at least 2 times half that number gives you that number. Okay, half of 98 is 49, right? So we know that 2 times 49 will give us 98. Okay, 2 is a prime number. It's good. We can't break it down anymore. 49, though, we can break down. Okay, two numbers that multiply to get 49 is 7 times 7. Okay, remember when you break it down, cross it out. Okay, can we break down 7s any farther? No. Okay, they are prime. We cannot break them down anymore. Only 1 times 7 will get you 7, and that would not break down the 7. We'd still have it, right? Okay, so now since it's broken down to its prime factors, we can look for pairs of numbers to take out. Numbers that do not pair up stay inside the radical. So it looks like we have a pair of 7s and a 2 staying inside. Okay, so remember the pair of 7s means the 7 comes out of the radical. What stays inside is what does not pair up. Okay, so there's the simplified form of the square root of 98, 7 square root of 2. So let's go and say x equals. Okay, which by the way, our units, what were they? Inches on this one. So we'll say 7 square root of 2 inches. Oops. All right, one more try. There we go. All right, cool. So yeah, let's try this last one. Alrighty, so yeah, starting with the Pythagorean theorem, c squared equals a squared plus b squared. All right, on this problem, looks like our hypotenuse opposite our right angle is 8. So that's what I'm going to plug in for C. A and B are the other two sides. I'm going to make x A, and I'm going to make this 5 square root of 2 B. Just remember, the whole 5 square root of 2 is being squared. We need to put parentheses around it. Okay, so yeah, 8 squared gives us 64. I'm going to bring down the x squared. Okay, here's, kind of the tricky part, but just remember, this power of 2 is being applied to both of these numbers. Okay, so 5 squared, well, let's not forget the plus sign, but 5 squared is 25. The square root of 2 squared, remember, the radical and the power of 2, square rooting and squaring, are opposites. They're canceling, and I'm just left with what's underneath the radical. So I'm having a 2 here. These are being multiplied. Okay, so let's go one more step and do that multiplication. So 64 equals x squared plus 50. Okay, now we can solve for x, subtract 50 first. Okay, looks like we're getting 14 equals x squared. Last thing is taking the square root of both sides. All right, here's the thing. Square root of 14 is not a perfect square, and they want us to simplify it and put it in its most simple radical form. So let's go ahead and break down 14 and see what happens. All right, so let me erase this. Okay, so breaking down 14 into its prime numbers, two numbers that multiply to get 14. Hopefully you're thinking 2 times 7. Okay, here's the thing. 2 is prime, can't break it down anymore, and so is 7. And remember, what we're ultimately looking for when we break down these numbers are pairs of numbers that get to come out of the radical like the 7 did for this one. On this one, we have no pairs of numbers. 2 does not have another 2, and 7 does not have another 7. So those are both staying in the radical, which would then multiply to get us 14. In other words, the square root of 14 is as simplified as possible. Okay, so some radicals cannot actually be simplified anymore. Okay, so that would be our answer. I'm going to go ahead and flip it around and say x equals the square root of 14. Okay, which, by the way, units, yards. Okay, so yeah, there's some good reminders on how to use the Pythagorean theorem, how to simplify radicals, stuff you've probably done, but it's been a while. So hopefully you guys are feeling good on that. I will see you later.